Good morning, class. Today we're going to get started on diodes. So we're sort of moving into the next phase of the course, taking the solid state physics that we've learned and now using it to determine how solid state devices work, and starting with the diode. The diode is a PN junction, and you can think of it simply as bringing together P-type and N-type material. So this would be the junction, and on one side it would be P-type, and on the other side it would be N-type. Now, for purposes of analysis, you can simply think that you've taken P-type and N-type and stuck them together. How you really make this thing is you take one or the other and you would diffuse in dopant of the opposite type. And maybe as we go through the course, when we get to the end, we can talk more about that process and how it affects this analysis. But for now, simply think that you've brought together the two pieces, P and N. Now, what happens then? Well, so you know what P-type is. There's lots of holes. And there's lots of electrons on this side. So naturally what's going to happen, I mean, you can sort of picture in your head things like if you had a blue liquid and a red liquid and you lifted a gate dividing the two or something like that, you're going to have electrons move over to that side, and you're going to have holes go that way. Now, what is going to happen? Well, okay, when a hole meets an electron, you can think of it that they just cancel each other out. I mean, the word annihilate maybe is a little bit too strong, but essentially that's what happens, because a hole is a missing electron. So when an electron meets a hole, it fills it and they both disappear. So what happens when you bring the P and the N together is that holes from the P side move over, and electrons from the N side move over, and they cancel each other out. And that goes on for a certain amount of time. Now, when they cancel each other out, they leave behind the dopant atoms. And so you have a layer on both sides of the junction where you've left behind, now remember P-type, that's acceptors. So you've left behind acceptors, which are negatively charged, and donors, which are positively charged. And this is called the space charge layer. Now, let me draw this here so that you understand. This is P-type, and this is N-type. And then on either side of the junction, which is where the P and the N met, you have a charged layer. Because now, the way to think about it is, all right, on the P side, there's acceptor ions everywhere, right? Okay, and on the N side, there's donor ions everywhere. But on the P side, there's also holes that, that can't, that match the charge of the acceptors, and on this side there's electrons. And so there's this region near the junction where all the electrons here have disappeared because they cancel with the holes, leaving behind the positively charged donor ion. And on this side, all the holes have disappeared, leaving behind. So, I mean, just to be perfectly clear, out here, there's acceptors and holes. All right, and out here, there's donors and electron. But there's no electrons here, and there's no holes here. And so in this layer, this space charge layer, you only have acceptors and donors, and so you have a charged region. And on the N side, it's positively charged, and on the P side, it's negatively charged. Now, you may be asking yourself, well, okay, how big is that? And this all fits together in the analysis we're going to do now, which is how you would determine how big that region is. So let's go on and do the electrostatic analysis, which may be a review for some people. And let's make our coordinate system. Naturally, x equals 0 is at the junction. And what we're going to define is we're going to define x sub n as the edge of the space charge layer on the N side, and negative x sub p as the edge of the space charge layer on the P side. So what I'm going to draw first is I'm going to draw the charge density rho. Now on the so this is negative x sub p, and on the P side it's negative, and its value is negative E n sub a. I had to put the E there to get charge from, remember, charge density is, this is charge per volume. Acceptor ions is number of acceptor items per volume, and so I multiply that times the charge on an electron to get the charge per volume. And on the N side, it's plus E and D. Now, jumping ahead, you sort of, I mean, it's sort of natural to come to this conclusion. This part equals that part because you have to have overall charge neutrality. So you must have that xp NA is equal to xn ND for zero net charge. Okay, so that's rho. I'll try to make my rho a little bit better here so you realize that's not E. The charge density. Now, now we'll start to answer the question of, well, how long did this, or how much did this process happen, leaving, how thick are these layers? Well, because there's this distribution of charge on either side of the junction, there's an electric field. And since you have positive charge here and negative charge here, there's an electric field that points in that direction, E. And if you think about it, since E points in that direction, it starts to inhibit the whole flow in that direction, and it also, inhibits the electron flow in that direction, since electrons want to go toward positive charge. And so what happens is the space charge layer gets bigger and bigger and bigger until the electric field is big enough to stop this process from happening, basically. All right, and we can analyze this by using electrostatics. So from electrostatics, you know that, okay, I mean, Maxwell's first equation, del dot E, the electric field, which, since this is just one dimensional, is dE dx is equal to rho over epsilon, the permittivity. And so I can figure out what the electric field is in this region. Now, for those of you that this is a review, you may sort of remember the picture here and remember how to figure it out. What I'd like to do is help you understand how to draw this next picture. And to help you, I want you to realize that, okay, dE dx is rho over epsilon. Everywhere rho is a constant, right? So that must mean that E is a straight line, because then the slope of E is a constant. So you can sort of figure out that on this side the slope is going to be negative, and on this side the slope is going to be positive, and they have to meet. Oops. I can draw, because you can't have a discontinuity in an electric field. And so there's sort of a E sub j in the middle of the junction. So the electric field E does this. And again, it's because dE dx of the straight line is a constant. All right, and so we can start to figure this out because we can figure out that that dE dx here. So let's do it this way. Let's do the P side. dE dx. Now, what is dE dx? Well, it's negative EJ over XP. Right? The slope. EJ over XP is dE dx. And on the P side, that's equal to the charge density on the P side, which is E minus E n sub A. Over epsilon. Sorry. So EJ is equal to E n A XP over epsilon. Now on the n side, you do the same thing. And on the n side, dE dx is equal to EJ over XN. And that's equal to, by Maxwell's equation, the charge density and I realize I'm kind of tightening things up in here, but so I'm going to solve for EJ from the n side, and I'm just going to put it up there. Whoops, that's supposed to be donors. because of course EJ equals EJ. And so you see that I can write down what EJ is in terms of either NA and XP or ND and XN, but since they're equal, of course they're equal. So it all fits together. So what I'm telling you is in this electrostatic analysis of a PN junction of a diode, I'd prefer if you try to work it through sort of graphically rather than start doing math. Because, I mean, the other way to do it is to do math and sort of solve this equation and stuff like that. And you tend to get messed up because of minus signs and stuff. So what I've shown you is a very simple way of determining what EJ is from Maxwell's first equation. Now the next step is voltage. Okay, and so since there's an electric field, there's going to be a voltage, V. Now, what is voltage? Well, E, right, is dV dx, minus sign. So V is equal to the integral of E dx. Now, don't worry about the minus signs and stuff like that. Just realize that V is the integral of E dx. And, the units all make sense, right, because electric field is volts per meter. So volts per meter times meter is volts. Okay, so now again, what I want to do in the electrostatic analysis of the diode is kind of try and use our smarts a little bit rather than relying upon the math. So what I'm going to do is I'm going to put x minus xp here. And I'm going to put x in there. Now, doing this at the board, it's helpful to be neat. And especially for those of you that are going to be taking the PhD qualifying exam later on this year, which I think they've rescheduled them for September. At some point, you're going to be doing your oral calls, and you're going to be standing up at the board, and you might be asked this question of deriving, the built-in potential of a diode. And so as you're doing this, the faculty sitting there are looking for a few things. Okay, so first of all, since E is dV dx and E equals 0 here, all right, that means that dV dx is 0 there. Of course, if V is, you start at 0. But when you start drawing this, I want you to make sure, and you have 0 slope right there. Now, what happens is that, well, okay, V is equal to the integral of E, and so it starts going up. And it goes as x squared. Now, on the other side, okay, what we're going to do is we're going to label something here. We're going to label something, what do we use for the label? Oh, we used now at xn, it's the same thing. The slope is 0 there because the electric field is 0 there. Remember, the electric field does this thing. So I want you to remember to start with the 0 slope. Now what happens is that, well, it goes down quadratically, and the two meet there. And of course the value and the derivative have to be continuous. So we can break the analysis down now, because we can call this V sub 1, and we can call this V sub 2. And of course VD is the sum of them, and that's what we're getting at. And And then we can sort of use our smarts and a little bit of pictorial analysis to figure out what V1 and V2 are. Because if you think about it, you would start there, and V1 would be the interval of E dx over that region. Okay, but I don't want you to plug in an equation here. I want you to just look. Okay, what is integral? Well, the integral is the area, right? So rather than, you see, because you have minus signs and stuff, so rather than try to do it mathematically, just realize that V1 is the area of that. And what is the area of that? Well, it's XP EJ over 2. Because that's the area of the triangle. And now we can plug in for EJ, and we'll use the EJ over here. And so, well, just writing it down, ENA XP squared over 2 epsilon. Now, V2 is sort of, you have to sort of think, contort your thought a little bit. V2 is, okay, imagining you're starting the integral here and you're integrating that way. And because, potentials start and stop wherever you want them to. And so basically, think of V2 as kind of just flipping this whole thing around and starting with the coordinate system there. And so V2 is the integral of E dx from xn to 0. Now again, if you try to plug in equations and do math, you're going to get all screwed up. Okay, but again, if you think of it pictorially, just realize that that interval is that area. Because that's what an integral is the area of a curve. So V2 is xn EJ over 2. And then plugging in, right, for EJ from here, that's END xn squared over 2 epsilon. And so the built-in potential V sub D is equal to V1 plus V2. And so it's equal to E over 2 epsilon times NA XP squared plus ND XN squared. And that sort of completes this electrostatic analysis of the diode. Now, that's that, and there's various other things that we could do here that we might want to do. For now, I'm just going to leave this the way it is and go on to our semiconductor physics more. So this is sort of electromagnetic analysis or electrostatic analysis of the diode, and it tells you, very quickly from the doping levels, okay, ND and NA, what the electric field at the junction and what the built-in potential of the junction is. Now, of course, everything's in terms of XP and XN. And you're like going, well, what is XP and XN? And what I'm going to do next is I'm going to show you that, well, what really is going on here is that this comes from physics. It comes from the solid state physics we've done. And so this V sub D is the fundamental quantity. And actually what you do is you do this all in reverse and you determine what xp and xn are from V sub D. All right, so let's determine what V sub D, the built-in potential, is. Okay, I'm going to erase everything here because I'm going to need the board. Now, the next step in understanding how to analyze the diode is to become comfortable with the concept of, well, it's called various things, but basically drawing the bottom of the conduction band and the top of the valence band versus X, versus position. So I'm just going to start doing it. And for those of you that this is a review, that's fine. For those of you that are new to this, we'll sort of back up and backfill your understanding a little bit as we go forward. Now, for those of you that this is a review, watch what I'm doing very carefully because, again, understanding how to draw these things takes you like 80% towards being able to get the right answer. So I'm first going to draw the draw E sub C. So what I'm drawing is the bottom of the conduction band in E versus K space versus position. All right, now, for those of you that is a review, think about this. That's minus XP. That's the edge of the depletion region. So remember, the slope is 0 there. All right. So now, these diagrams, like I'm going to draw right now, just because, you know, remember when as we've been drawing E for solid state, for band structure and stuff, we've always drawn E is going up, meaning higher position is higher electron energy. But remember, an electron is negatively charged. So potential, because of Ben Franklin, you know, is going to go the opposite. Okay, you see, because the potential here, this is a potential for a positively charged particle. So for an electron, which is a negatively charged particle, what I'm going to draw now is going to be the the reverse of that. So basically, it's going to curve down and go up, go down over like that. Now, the next step is you draw X of n. And actually, I need more space here. So this is minus X of P, and this is X of n. And again, the slope is 0 there, because the electric field is 0 there. Now, the next step is, okay, so now, just sort of getting everything straight. Okay, we have, you know, we have our junction here. This is X equals 0. And on this side it's N type, and then, I'm sorry, this side it's P type, and on that side it's N type. So what we're going to do first, well, or what we're going to do next is, okay, this is N, and we're going to draw the top of the valence band now on the N side. So remember, this is E sub C. And again, for those of you that are kind of trying to connect this with E versus K, it's like, I don't know if I want to draw it because I don't want to confuse. It's like we're drawing the bottom of the valley thing as a function of position, and the top of the valley thing as a function of position. So let's just leave it at that because I don't want you to get too confused. All right. So on the N side, remember if it's N type, all right, where is the Fermi level? Well, the Fermi level is close to the conduction band, right? Now, so here I've drawn my N-type material. Outside of the depletion region, the N-type material is just N-type material. It doesn't know anything else than that. It just thinks it's home. It doesn't know there's a diode over here. So there's an EV, there's an EC, and there's an EF. And EF is closer to E sub C because it's N-type. Now, the next thing you do is you realize that what EF means. And since EF is our Fermi-Dirac statistics, it represents kind of an equilibrium energy for the entire system. And so EF is a constant. Yeah. Okay. I haven't drawn it very well, but let me fix it when I'm done here. So the next step is you draw EF as continuous across the whole thing. Now, that means basically we're in equilibrium, and so Fermi-Dirac statistics across the whole thing is obeying the same Fermi energy. Okay, don't worry about it too much. Now, let me fix this over here a little bit, draw it a little bit shorter. So you kind of have to remember what you're doing. All right, and now what I'm going to do is I'm going to draw, put that over here, the P side. Now on the P side, right, this is E sub V, and the Fermi level, EF, is closer to the valence band. And then you basically just connect everything, trying to draw it well. And realize that this, the band gap, has to be the same all the way across there. So what I'm trying to impress upon you is that being able to draw this is like, it's half the battle in answering questions about diodes. And so I want you to, sort of, follow my lead here and understand how to draw a good PN junction diagram, because it just helps you out understand everything. So basically, it's following this quadratic kind of behavior here for both the bottom of the conduction band and the top of the valence band. EF is this energy that's constant throughout the system, and that's it. Okay, that is what we call the band structure diagram for a diode. And again, for those of you taking the quals, and if I ask you this question, that better be zero slope there, okay, showing that you understand the meaning of the whole thing. All right, so that's our diode, and at this point we can start analyzing it because we know how to. And what we want to find out is what is V sub D. Okay, now look at this carefully. That is equal to that. Now, okay, one word of kind of just making sure you got everything. This is an energy diagram, whereas this is a voltage diagram. Now, to connect the two, energy is charge times voltage. You just put E there. Now, because we usually think of energy in solid-state devices in physics in terms of electron volts, it's the same number. So, like if this is 0.7 eV, this is 0.7 volts. Okay, so at the same time, you don't need to worry about it too much. You don't need to think about it too much. It's the same number on both diagrams when you use electron volts as energy. Okay, so we would like to know what V sub D is, and we can start doing that because we can look at the diagram, and we can do it because we've drawn the diagram very well, and we can figure it out. And we can figure it out because, okay, let's do over here. This is the gap, right? So if you think about it, EV sub D is equal to the gap minus this part, EC minus EF, minus that part, which is EF minus EV. Right? You can just look at it pictorially and figure this out. Which, by the way, I mean, you could do the same thing on the other side. You could, you know, because this, of course, is also E sub D. So, however you need to do about it, you know, I'd like you, perhaps now, you know, you could pause the lecture and just sit there and draw this by yourself and go over and make sure that you are good with the fact that the built-in potential, right, the extent of this curvy part is equal to the gap minus this minus that. Now, you're probably like, hopefully thinking ahead a little bit and now kind of like connect in what we've been doing for the last few lectures because remember, these quantities mean something really important to us, right? Because we know that, okay, now here you have to, I'm going to write down equations and you have to remember what side you're on, P or N. Okay, so let's do it this way. On the P side, right, on this side, okay, P is equal to N sub V times e to the negative EF minus EV over KT. And we're going to go further and we're going to try to make that better. And we're going to assume that both our doping sides are kind of pretty well doped, much higher than the intrinsic level. And so this is P is approximately equal to N sub A. All right, and the same thing on the N side, right? N is equal to N sub C times e to the negative EC minus EF over KT, and that's approximately equal to N sub D. All right, let's. So now what we're going to do is we're going to use these and plug in basically, and finally we'll do one more thing, right? Remember, N times P, it doesn't matter what side you're on, is NC. Well, okay, just let's go ahead and do it so that we reinforce our understanding of what NP is. Now, so I'll write down negative. Now again, do this at home, and you see since this has a positive EF, that cancels that one. So this becomes negative EC minus EV. This is a review right now, we've covered this. So that's equal to NCNV in the negative E gap over QT. But of course, that's equal to Ni squared, as we've gone over, because NP is equal to Ni squared always. So you can kind of see what's going to happen now. We have a formula for the built-in potential. In terms of E gap, well, that's going to come from this equation. In terms of EC minus EF, well, that's going to come from this equation. And EF minus EV, and that's going to come from this equation. So what I'm going to do now is erase part of over here, but I'll leave the built-in potential diagram. So we can sort of see the connection between them. So putting that together, I did this just before I started here. Let me just keep. Because I did it with a different flow, but let's go ahead and see if it works right. Okay, so E gap. All right. So E gap comes from this equation. And so, if you think about it, what we're going to do is, I'm going to skip some steps. Sorry. We're going to put e to the minus e gap. We're going to put that on the other side, so we can write that E gap is equal to KT logarithm of NCMV over Ni squared. Right? And let me do it this way. So I'm going to. So I hope everyone followed that. If you didn't, pause the lecture right now and see that you can take that equation and solve for E gap equal to that. Now let's do this one. EC minus EF, that comes here. And it's the same sort of thing. I'm going to put the exponent on the other side. And so EC minus EF is going to be KT times natural logarithm of, think about it, you put it over there, NC over ND. Okay, and again, if you didn't follow, how I did that in my head, pause the video and do it on paper. And then finally, this one here, EF minus EV, which comes from this one. We're going to put the exponent over there. Okay, KT natural logarithm of NV over NA. So Now we can put it all together. EVD is equal to, I mean, I could bring the, actually, let me, sure, okay. Let me bring out the KT, EVD, because all these have a KT in front of them. So first there's E gap, so that's the natural logarithm of NC NV over NI squared. And then I'm going to subtract off here natural logarithm of NC ND over ND. And then this one here, minus ln of NV over NA. Okay, and those of you that are comfortable with natural logarithms can already see the answer probably. Because, okay, let's work it. I mean, basically you use that ln of A times B is equal to ln of A plus ln of B. I mean, we can walk through it. EVD over KT is equal to ln NC plus ln NB minus ln of NI squared. Right, because the corollary of this is, you know, ln of A over B is ln A minus ln B. Okay, so that's that one. And then we'll do minus, okay, I'll put that way. Minus ln NC minus ln ND. And then minus ln NV minus ln NA. And so I'll go ahead and just go ahead and get rid of the NC. So here's an NC, and that subtracts that one. Here's an NV, and that subtracts that one. So you get rid of those. Now, this one turned positive. And that one's positive too. Okay. Minus. Okay. And then I'll just collect them. So EVD is equal to KT. Now I'm going to do this in reverse. Natural logarithm NA ND over NI squared. So what I've shown is, okay, what I've shown is these are really important, right? Okay, and that's why we spent so much time on them. Understanding that you can get P and N from the position of the Fermi level, multiplying times the effective density of states. And then especially when you can make the approximation that P is NA and N is equal to ND, it enables this whole thing. So basically what I'm showing is that the built-in potential is determined directly by NA and ND. NI is a property of the material, of course. So the doping level on either side determines what d sub d is. So this is actually where we start. And you know, to a certain extent, it would be better to start here and then do the electrostatic analysis, because then you would see from the very beginning that this is the fundamental quantity. Now, the part of the electrostatic analysis I left showed that VD is also equal to this, right? But all that means then is that I can determine V sub D from the doping level, and then I can use that in those equations I erased. Xn ND is equal to Xp Na. So if you look at it, I can then solve for either by plugging in either Xn or Xp. Now I'm not going to do that. I just wanted to show you, how this works. So basically, PN junction, a diode, has a built-in potential that is determined by the doping levels, and then you can use electrostatic analysis to determine what the width of the depletion region is, Xn or Xp. All right, so that's the end of this lecture. And so this lecture was basically electrostatic, or well, no, I'm sorry. This lecture was what you would call equilibrium properties of a diode. What that basically means is when it's just sitting there on the table not doing anything. The next thing we're going to do is we're going to hook up wires to it and put on voltages and see what current flows. So we'll start that in the next lecture, and you'll see that we use this diagram in order to calculate how current starts to flow when you put a voltage on either side of the diode. And that's, of course, the diode equation. And that's what we're basically going toward. Okay, so that ends this lecture.